Okay, to follow up with the reaction laws that we were dealing with in the last section, we have to look at something called orders of reaction. And orders of reaction describes how many of the actual reactions are involved in determining how fast the reaction goes. Now, as I had said earlier, it's possible to have 1, 2, or even 3 reactants here. But generally you just look at 1 or 2. Most of the orders of reactions will be 1 or 2, but there are some 3 as you see here. But for the rest of this chapter, most of the ones that we're looking at are first and second order reactions. And of those 2, the first order is the most common. So, what's a reaction law? Is simply a formula that we use to describe how fast a reaction can go and how we can predict that to be the case. Now, as it says here, the rate of reactions are reliant upon the concentration of the reactants. The more reactants we have, the more collisions you're going to have, and therefore the rate of reaction will be greater. The temperature at which the reactions are run, which means if the temperature is increasing, the molecules are moving faster, colliding harder, faster rate. If it's cold, it'll go slower. And the surface area of the reactant. So if we have a lot of surface area, it means there's a lot of places of contact for the collisions to occur. The more surface area, the more the reaction is going to go, and more quickly. If it's kind of balled up instead of all out there, it'll be just the opposite. And so what we have to do is we find some way of observing these things to take place. So we run a series of experiments where we can actually see the reaction take place in a timely manner, or put on computer camera and slow it down and be able to measure through that. A rate law is represented by this formula here. R equals K times A to the M power times B to the N power. There could be a C, that'd be the P power, but that, again, that's fairly rare. So we just go with the A and the B part, or whatever the 2 concentrations are. This K right here is called a rate constant. And a rate constant is any constant, usually has labels that don't make a lot of sense. Some do, like slope. Slope is a rate constant in a y equals mx plus b situation. In this case, the labels here are just going to tie the 2 parts here. Rate is moles per liter, and these are concentrations, so per concentration, which is moles per liter, moles per liter. So they'll tend to cancel out. There'll always be a second denominator, but we'll get into that later. But we can calculate, if we know the rate, we know the concentrations, and we can calculate the amount that the constant is, and from that we are going to be able to figure out or predict either rates of reaction or particular concentrations under certain conditions. This is why we like using math equations, because math equations simplify actual data that we see, that we observe, and we can fit it into some kind of graph like we've shown so far, and come up with a mathematical equation based on that. So when we're looking at a rate law, we have to understand it's coming from a series of experiments. So they have to run many experiments where they change things up, change concentrations, see how it affects the rate, and they finally come up with this collection of data which they graph, and from the graph we're able to do various mathematical manipulations to come up with a straight line, and from that straight line we're able to come up with an equation. And that'll be something that we're going to talk about in the next lesson after this. What we're doing now is just going through the basic ideas on where they come up with these numbers, and then we'll actually do some look at data to figure out how the equation works out. So here's the first example we're going to deal with. A rate law is defined as R equals K times NO squared times the concentration of NO2. What is the order of each reactant? So these are, when they write rate laws, they're only dealing with reactants. They never deal with the products. So these are 2 reactants, and their exponents determine the order of those reactions. in terms of those particular reactants. And this is what is the overall order of reaction. So, since the exponent here is 2, we say that this is second order in terms of NO. Since the exponent here is not written, we understand that this is assumed to be 1. So this is considered to be a first order reaction in terms of NO2. Then the overall order of reaction is the sum of those two exponents, 2 plus 1, which would give us 3. So this is a third order reaction in terms of the overall reaction. It's a second order reaction in terms of the reactant NO, and it's a first order reaction in terms of the reactant NO2. It's that simple. It's just a basic observation and addition for the overall. So this time we'll give you an actual reaction, and that is the production of NO2 from NO and O2. Now the reason why I'm using this example is because a lot of times people will think that because this has a 2 in front, that becomes an exponent over here. And there's no correlation between the equation coefficients and the exponents. So when you are being asked to find out the order of reaction in terms of each reactant, you look only at the exponents here, you ignore the equation. That's why I didn't put it in the first one, so it didn't give it away. Sometimes it's the same, in fact a lot of times it's the same, to be honest, but sometimes they're different. In this case they're different. So what is the order of reaction in terms of each reactant? The first reactant is NO, and the exponent for that is 1, so this is first order in terms of NO. We have a 1 for an exponent for the O2, so it's first order in terms of O2. So we have first order, and then the overall reaction is the sum of the two exponents, 1 and 1, which is 2. That is the second order reaction. So your practice problems on page 640, do problems 39 through 42, all of them. It won't take you very long. It's very simple. Good luck.